Hey, so if you're asked to do a resource sheet, this is all the rest of the identities. So we've done, what is it, 17, 9 plus 8, 17. So this is 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. That's it. So that was my plumber. So today we're not going to look at all of them. The first little batch we're going to look at are these four. So you will not be expected to know how to use these tan compound angle identities. So these ones are called compound angle identities. And we're also going to look at these four, which are the double angle identities. Again, we're going to ignore tan for the time being. I will put that in the next lesson. I have the unit circle here because we will be using the unit circle, so I need that to refer to. And pause here if you need to do any writing down. Here are the first questions. So I'm going to do A here, and I've set it up so that I still have the compound angle formula sitting when I go to do B. I don't know how much room it's going to take, so I've spread it out a little bit. I'm going to put this on page width, and I think I can get rid of B, which we're not going to look at today. Sorry, we're not going to look at it right away. We're going to look at A. So the first question is to determine the exact value of sine 165 degrees. So at least it's in degrees. The one that I erased was in radians. So if I go to the unit circle, there's 150 degrees, there's 180 degrees, 165 is sitting in between, so there's no measurement, and that's the problem. And that is why these compound angle formulas are available to you. Now, let's take a look at them before I start writing. The top one and the bottom one, sometimes they get mixed, and I'll write it here in a second. And the top one, plumber, there's time for a pause. Okay, let's try that again. So, sometimes when you're looking at textbooks, and I think this is where I was at, sometimes when you're looking at textbooks, you will see, and I'm going to do this on 2 lines just because my writing is big, sine x plus minus y, so it kind of bulks these two together, in which case if you follow the right-hand side, they both have sine x cos y, so sine x cos y, and then behind the sine they have cos x sine y. But if you notice, the plus stays with the plus and the minus stays with the minus, so that means the plus minus stays plus minus, and they bulk them together. Similarly, with cos x plus minus y, they both have cos x cos y on the right hand side, and after the sine it's sine x sine y. But if you notice, cos doesn't maintain its sign, so this plus minus has to flip into a minus plus sign. So you may see this in textbooks in your future. You may also see it with A's and B's rather than X's and Y's, likely capital A's and capital B's. That's probably the most common thing I've seen. So back to this question, the problem with this is that we have a degree measurement that's not on the unit circle. So our job is to take the red sine x plus y or sine x minus y and create 165 degrees using numbers off the unit circle. So you can take 2 numbers off the unit circle and add them to make 165 degrees. You can take 2 numbers off the unit circle and subtract them to make 165 degrees. And there's lots and lots and lots of combinations. Your answer will be subtly different, but mathematically the same. Oh, there's a hockey reminder. So let's see if we can find a way to create 165 degrees. So I am going to go with sine, I'm going to say 130. Oh, maybe I should check that. Nope, can't use 130. Can use 135 degrees plus 30 degrees. So those are two numbers off the unit circle that when added, I can create 165 degrees. So you may find a minus version that you quite like. Now something that's not allowed to happen, so I'm going to write it down and then I'm going to erase it immediately. You are not allowed to do this. This does not exist. This type of thing, to create that, nope, doesn't happen. Really common, because you want it to happen, because it's super familiar, but the thing is, in order to use a compound angle, an arrangement of two angles being added or subtracted together, you have to use one of these four guys. So I've actually used the top one just to specify. I've found two angles being added together, so I have to use the right-hand side of the top one. So the x, I have designated 135 degrees, and the y is now 30. So my next line is sine 135 degrees, because that's the x, cos y, so that's the 30 degrees, plus, because it goes with plus, cos x, so cos 135 degrees, times sine y, and y is 30 degrees. And so now what happens is you have this to pluck off the unit circle, you have this to pluck off the unit circle, you have this that you can get off the unit circle, and you have this. So you're going to replace all four of these things, and you're going to place them with numbers from the unit circle. So that means that box is going to turn into some little fraction. This box is going to turn into some little fraction. Plus sign. This box, some little fraction. This box, some little fraction. So let's see what those fractions are. So remember, sine is the second one. Here's 135 degrees. So I am going to use root 2 over 2 to replace, this entire box of information. Then I move on to cos 30 degrees. So 30 degrees is here. Cos is the first one, so that's root 3 over 2. So I can replace that entire box of information with root 3 over 2. Then I have to go back to 135 degrees, and I have to pick cos, and cos is the first one, so negative root 2 over 2. And finally, I have to go back to 30 degrees and pick sine. So here's 30 degrees. Sine is the second one, so I select the 1/2, and I replace the box of information with a half. So now you need to figure out how to deal with fractions. So a reminder that when you're multiplying fractions, you multiply across the top, you multiply across the bottom. So I can multiply those two and those two. I have to take a break with this plus sign. I multiply those two and those two. So root 2 times root 3 is root 6. 2 times 2 is 4. Plus negative root 2 times 1 is negative root 2. 2 times 2 is 4. Now we're adding fractions, so we need a common denominator. Aren't you excited that we actually have a common denominator here? Now, to be honest, if you use the special triangles, you won't have a common denominator, so this is super advantageous to use the unit circle. So I'll have root 6 plus negative, so that's just minus, root 2 over 1 big 4 rather than split, and I'm just going to sum it up with a tidy little therefore statement. So next step is to do this all again with cos and 5 pi over 12. So maybe you don't know what 5 pi over 12 is. So that's where we go back to the degrees to radians, radians to degrees. And we will get 180 times 5 divided by 12, ignore the pi's, and we get 75 degrees. So maybe you like to think in degrees over radians. I know I do. And if I check the unit circle again, there's no 75 degrees. So I have to create 75 degrees using two numbers from the unit circle so that I can use one of these two identities to break it up. Doesn't matter if you add or subtract. If you find two numbers that add to 75, you're going to use the top one. If you find two numbers that subtract to make 75, you're going to use the bottom one, cos specifically. So I'm going to keep this simple and use 45 plus 30. I know those are both on the unit circle. And while I'm here, this is the cos plus version, so I must split it up like this. So cos 45 degrees is the x, cos 30 degrees is the y. When we start with plus, the other side of the identity says to use a subtraction sign, and then it's sine of x, so sine of the first angle, which is 45 degrees, another sine of 30 degrees. And then we're going to have to bop back and forth between this page and the unit circle, unless you've got it memorized, and we can find that box of information, that box of information, take a little break, that box of information, that box of information. So again, we're going to have 4 fractions in place of those boxes. So cos 45 degrees. 45, cos is the first one, root 2 over 2. Cos 30 degrees. 30 degrees, cos is the first one, root 3 over 2. Minus sine, because that's the formula. Sine 45 degrees. Sine is the second one, so root 2 over 2. And finally, sine of 30 degrees. There's 30, sine is the second one, 1/2. So then we can do our fraction part again. So multiply across the top and the bottom, multiply across the top and the bottom. So that's root 6 over 4 minus root 2 over 4. Common denominators all set for us. So that's root 6 minus root 2 all over 4. And if you're thinking, oh wait, I remember that one, that was the exact same answer as this one, it should not surprise you. I mean, if you use the unit circle, you're going to get a bunch of root 6s and root 2s and 4s because you're repeating the use of the unit circle numbers. So sometimes it'll be pluses, sometimes it'll be minuses. It's a combination of what it can occur. So this could be minus, this could be minus, they could both be plus, you could have one of each. It just happened that both of these have the exact same answer. That is purely a coincidence and in the pattern making. So next questions, also using the compound angle identities. So I'm going to move 3 out of the way for a sec. And we're going to look at this, and the question says, express in terms of sine x and or cos x. So that means we're going to have to match this statement up with one of these. Hopefully you know to look at the bottom two because it's cos, and then look at the bottom one out of those two because it's cos with a subtraction for the compound angle. That means I can use pi over 6 for x, and I can use x, not negative x, just the x for the y. And although that might be a little bit confusing, it's just first entry, second entry. That's what these mean. So cos of your first entry, cos of your second entry, minus means plus, sine of your first entry, sine of your second entry. And although I've mixed this up a little bit, we should be able to find that on the unit circle, and we should be able to find this on the unit circle. I can even do it without turning it into degrees because I know that pi over 6 is on the unit circle. So I need to go to the unit circle, find pi over 6, and then pick cos, which is the first one, so root 3 over 2. So I'm going to replace that with root 3 over 2. I can't replace cos x, so I leave it. Plus sine, go to sine pi over 6. So we're still at pi over 6. Sine is the second one, so that's a half. Now there's quite a few different answers for this question. Number one, I would take off the brackets and you could write it like this. Another possibility would be, you notice that, oh, the first half is over 2 and the second half is over 2. So you could write root 3 cos x plus 1 sine x, all of it over 2. There's a whole bunch of different possibilities for the most clean and simplified answer. There is even common factoring out a 1/2 and leaving the root 3 cos x plus 1 sine x. So there's a multitude of different answers. So a question like 3 is actually one of my favorite kinds of questions because, as I said when we first started trig identities, if you have a sense of what these look like because you use them repeatedly, you will likely have an easier time with it. So knowing that there is a cos identity that takes two angles being subtracted in your list is a good thing. Now, this one's a bit different in that we've got the stretched out side. We've got this side of the question, and we have to best match one of those and then work backwards, even though there's no backwards and forwards. So can you see which one it most closely matches? It should most closely match this one at the bottom because it's got a plus sign, or this one at the top because it's got a plus sign. So it's one of those two. Can you figure out that it's not the bottom one because the bottom one goes cos, cos, sine, sine, and this one alternates? So although it's going to take me a minute to deal with this, the first thing I would do is play a little matching game and turn this around so I've got the sine multiplied before the cos in the first half, and then I've got the cos multiplied before the sine in the second half. Now notice the sine 5a stuck together and the cos 2a stuck together, and the same up here. Now hopefully you look at that and you can say, okay, you know what? That pretty closely matches this one. So I've got sine x, and x is 2a, and it's also x is 2a back here, and y is 5a, and y is 5a back here. So I've pretty closely matched that, which means I can steal the other side, and I'm going to write it in space and drag it around in a sec. But I can steal the other side where I can write sine x goes first, which is the 2a, plus y goes second, which is the 5a, and then I can tidy that up and say sine 7a, and that is as simplified as you can possibly get. So bear with me for a sec while I do my little drag and drop. Oh, this is working well. Not so well, I jinxed it. So there. The rearrangement, in case you can't see it really clearly, the simplifying, and the final simplification. Okay, so I'm going to take a little bit of a break because we have one last question to do with compound angles, and then we're going to move on to talk about these guys, which I'm going to erase this page, delete page. We're going to talk about the double angle identities. So I know there's 2 of them, and I promised that there was 4 of them, but I'm going to show you how to take these 2 and generate the other 2. So I'm going to leave this here while I pause, see if you can tackle this. This is a left side, right side question because it says prove. Catch you in a minute. Okay, time's up for my break. So what I did was I set up the left side, right side. The right side, I can't think of anything to do. It's already in sines and coses, and it doesn't look like anything I recognize, as opposed to this side, which this thing looks like this thing. And what other color do I want to use? Blue. This thing looks like this thing. I mean, it's exact. So I'm going to color code this a bit. I'm going to take sine x plus y, compound angle, and I'm going to do the stretchy side, which is not a technical term. So sine x cos y plus cos y sine x. Oh, cos x sine y. My hand did it, my mouth didn't. Plus sine, that's this plus sine. And then I'm going to dig out blue just for the color coding. And I'm going to take this, which is sitting here, and stretch it out. So sine x cos y minus cos x sine y. So we have to figure out, just like all the other identities, how we're going to make the left side equal the right side without faking any math. Can you see it? Can you see that here is a positive cos x sine y, and here is a negative cos x sine y, so they will make 0 cos x sine y's. And here is a sine x cos y, one of them, and here is a positive sine x cos y, another one of them, and when I add one of them plus one of them, I get 2 of them, and if I'm not mistaken, that is exactly what's sitting over here. So this didn't take much work at all, except finding information to replace. And we're done. So a reminder that after a little bit of work with exact values, we still have to worry about left side equals right side. So the next thing is taking these 2 double angle identities and making sure that we can get 4 out of them. So we're going to take care of this. Now, before I go on, I want you to know that there is only one double angle identity, and I will show you how it works in a minute. There's only one double angle identity for sine 2a. But if I flip back to this sheet, you'll see that there's 3 double angle identities for cos 2a, which means you always have a choice. And when I say you always have a choice, sometimes the choice is the fastest way, and sometimes the choice is not the fastest way. So we'll deal with that in a minute. What I do need you to remember is this one. So that's the one that's handy to memorize. It looks a whole lot like my favorite, which is sine squared x plus cos squared x equals 1. And what I do want you to know is that, my favorite, is useful in generating the others. So off to the side, I'm going to remind you that sine squared x plus cos squared x equals 1 was a Pythagorean identity, and there were 2 identities that you could generate from that you didn't necessarily have to memorize, but were true. So here's what you can do, and there's 2 ways to do this, which gives you the 2 other formulas. First one, if you pick up that cos squared a and turn it into 1 minus sine squared a, and leave this minus sine squared a, you'll get that statement, in which case cos 2a is equal to 1 minus 2 sine squared a. So that is this one. Then you can do the backwards of that, where you can take cos 2a equals, leave the cos squared a minus, and then we need to take the sine squared a and turn it into 1 minus cos squared a. But that needs to sit in a bracket because it comes after a minus sign, which means I have to multiply through a negative, and then I can collect cos squared a plus a second cos squared a is 2 of them, and you get this one. So you can make 2 out of 3 of them as long as you've got a little bit of memorization for the day that you might have to memorize this list. And remember, there are 28 of them so far. So now I want to take a little break from this. So we're not doing any questions yet. I want to show you how this blue thing works. So this blue. This is a double angle identity. Basically, you have a double angle and can split it up into single angles. That's what this does for you. So if I go back to that statement and I pick a different double angle and I pick something like sine of 6a, this 2 is forever a 2, but you can take half of 6, which is 3, and put 3 a's there and the other 3 here. This is how this double angle identity works. So I can pick any even angle. So sine, I don't know, 34x. The 2 stays there. I have to find half of 34, which is 17. So 17 of the x's goes there, and 17 of the x's goes there. And you can do this all the way along. And before I forget, I don't know if you remember back to the original trig identities note where I said you couldn't just take these squareds and randomly stick them downstairs and make them non-squareds. So I told you that this and this were completely different things. Now you might know why, because you actually have a 2a or a 2x or a 2 something. So the next thing I want to look at is these 3, as in this one, which is another double angle. So whatever's here, half of it goes there, half of it goes there. This one, half of it goes there, the other half goes there because there's actually cos a written twice. And this one, same deal because it's squared. So I'm just going to pick another number here, another color. If I have cos 6a, just to maintain this, I could write cos squared of 3a minus sine squared of the other 3a. So that's how this splits up. The other option is that we do 2 cos squared of the 3a. 3 of them are with the first cos, 3 of them are with the squared, minus 1. Or you have the option of 1 minus 2 sine squared 3a. And you can do this for anything. As in, I'm not going to use 34 just to mix it up a little bit for myself. So I'm going to pick 18. So cos 18x. As long as it's even, I can split it in half. So 9 of them go there. 9 of them go there. The other option, 9 of them go there. The other final option is not cos. It's sine. 9 of them go there. So that's a brief once over of how these split up. Most often you will see literally the 2 with an A or an X or some other letter. I am going to leave this up while I unhand cramp. And we're going to continue with the proving left side equals right side. So when you come back, or when I come back, I'll have this split so we can deal with it. What's under this box? My list of double angles. Because will you look at that? Double angle. Single angles are friendly. It doesn't matter that it's tan, it's that it's friendly. So I will be back with you in a moment after my hand cramp goes away. So she's going to cramp up again soon, I can tell. But what I did so far is I took my friendly side, my single angle side, and I did this. Do you remember why? Do you remember where I got this from? This is one of the quotient identities. It's the quotient identity that replaces tan x. So I made it sine x over cos x because I still feel very strongly that sine and cosine are your friends and tan is not. So now what we have to do is we have to start replacing on this side. So I chose not to write it down as it was, and I need to find replacements because this is not a good thing and this is not a good thing. So if you look at sine 2x, there's only one replacement that you can use, and that is that sine 2x can be replaced with 2 sine x cos x, which actually makes me fairly happy because my right side has a sine x in the numerator, and now so does my left side. Unfortunately, my left side has a whole bunch of other stuff that I don't need there, but at least I'm going in the right direction. So here's the thing about the denominator. I'm going to put down the 1 plus, but I have cos 2x, and the unfortunate business about this cos 2x is you could replace it with this one, you could replace it with this one, or you could replace it with this one, and they're all perfect. But you need to replace it with the fastest one. So what I'm going to do is I'm going to look to the right side for hints, and the right side says, please have coses on the bottom. So that means this middle one isn't a really great choice. Can you tell which other one isn't a really great choice? It's this one, because this one has some sines in it. This one is the best choice because this bottom choice has only coses. So I'm going to put that in, and I don't even need brackets because it's following a simple plus sign. I need to do the hard work of making sure that it's an x and not an a. Do you see why that's good for a second reason? 1 minus 1 is 0. I'm going to have a line of neatness. So my top remains the same. And my bottom is 2 cos squared x. And do you see how that leads us in the right direction? And it's all multiplying and dividing now. There's no adding and subtracting. So I can do 2 divided by 2 is 1, and I'm going to make that invisible. And this cos x I can cancel with one of the two cos x's here. So what ends up happening is that I end up with sine x in the numerator and cos x in the denominator, and ta-da, they match, because they always match in this class. And then we have the last one for today. Now, I hope you look at this question and there's something about this question that you dislike. I know there's something I dislike, and it's this. So what I'm going to do is I'm going to show you how to do a replacement for this, especially if there's something that you don't like. And the truth is, some of you are probably doing it already, but you're doing it semi-illegally. So I'll show you how to pull it off correctly. Give me a pause. So I'm hoping that you and I dislike the same thing, and that is this x over 2 business. So what I'm going to do is I'm going to take that x over 2 and replace it with something else that doesn't have anything to do with x's, so that's important. So I chose the thing that's in most of the textbooks, and that is an a, so it looks a whole lot like the a's. Now, the thing is, you can't just do that. You can't just pluck up something you don't like and stick in something you like better. I mean, that's totally not legal, unless you can figure out how to do it mathematically. And that means that if you change an x over 2 on this side, you have to make mathematically correct statements on the other side. So we have to take the left side, and instead of writing the x's, we need the mathematical equivalent so that this will follow from our replacement. So I'm hoping you guys have some knowledge of fractions that will let you pull this off. Maybe it's going back to putting a 1 under here and then cross multiplying. So if you do cross multiply, you get 1x equals 2a. 1x equals 2a, so that's that cross multiplying from rational variable expressions, among other things. That means this x must be mathematically replaced by 2a, and this x has to be mathematically replaced by 2a, and everything flows from there. So I can take this tan a, and I can make my fairly easy logical switch, which is that. And on the left side, sine 2a has only one replacement, which is a good replacement because now I have a cos a on the bottom, whereas I didn't before. I need to put this replacement in a bracket because it's following a negative sign. So I need to know which one of the 3 replacements is best for this. So I need sine a's on the top, so I want the quickest way there. So this one's okay because it's got sine a's. This one's the best because it's all sine a's. So 1 minus 2 sine a squared. 1 minus 2, sine squared a. And then if I run that negative through, it changes signs. So this is the quickest way. And I remember saying to you in the trig identities note that the more of these you do, the more they remind you of other ones you've done. So this reminds me of the one that we just finished. We made selections based on the same criteria. 1 minus 1 is 0. So line of neatness, 2 sine squared a over 2 sine a cos a. It's all multiplying and dividing, so my 2's can cancel out, and one of these sine a's can cancel one of those sine a's, so you end up with sine a single one on the top, and a single cos a on the bottom, And it is not a coincidence that your left side and your right side look the same, because that's always going to happen as long as you do real math. So that is a combination of compound angle identities and double angle identities. It still means that we have to deal with this one, and we also have to deal with these two. And there is something else I want to show you, but I figured it would be a good idea, even though it uses possibly any of these 8, I figured it would fit nicely with the day that goes with this, or the lesson. So the following lesson will be, I think, the last lesson of the Identities unit, and then it'll be test time, assessment time. And again, a reminder that this stuff doesn't go away, and you are here for a reason. I'm not sure what that reason is, but you can figure that out. So bye for now.